This right here is a picture of René Descartes. Once again, one of the great minds in both math and philosophy. And I think you're seeing a little bit of a trend here that the great philosophers were also great mathematicians and vice versa. And he was somewhat of a contemporary of Galileo. He was 32 years younger, although he died shortly after Galileo died. This guy died at a much younger age. Galileo was well into his 70s. Descartes died at this is only at 54 years old. And he's probably most known in popular culture for this quote right over here, a very philosophical quote, "I think, therefore I am." But I also wanted to throw in, and this isn't that related to algebra, but I just thought it was a really neat quote, probably his least famous quote, this one right over here. And I like it just because it's very practical. It makes you realize that these great minds, these pillars of philosophy and mathematics, at the end of the day, they really were just human beings. And he said, you just keep pushing. You just keep pushing. I made every mistake that could be made, but I just kept pushing, which I think is very, very good life advice. Now, he did many things in philosophy and mathematics, but the reason why I'm including him here as we build our foundations of algebra is that he is the individual most responsible for a very strong connection between algebra and geometry. So on the left over here, you have the world of algebra. And we've discussed it a little bit. You have equations that deal with symbols, and these symbols are essentially, they can take on values. So you could have something like y is equal to 2x, y is equal to 2x minus 1. This gives us a relationship between whatever x is and whatever y is. And we can even set up a table here and pick values for x and see what the values of y would be. And I could just pick random values for x and then figure out what y is. But I'll pick relatively straightforward values just so that the math doesn't get too complicated. So for example, if x is negative 2, then y is going to be 2 times negative 2 minus 1. 2 times negative 2 minus 1, which is negative 4 minus 1, which is negative 5. If x is negative 1, then y is going to be 2 times negative 1, 2 times negative 1 minus 1, which is equal to, this is negative 2 minus 1, which is negative 3. If x is equal to 0, then y is going to be 2 times 0 minus 1. 2 times 0 is 0 minus 1 is just negative 1. I'll do a couple more. If x is 1, and I could have picked any values here. I could have said, well, what happens if x is the negative square root of 2? Or what happens if x is negative 5 halves? Or positive 6 sevenths? But I'm just picking these numbers because it makes the math a lot easier when I try to figure out what y is going to be. But when x is 1, y is going to be 2 times 1 minus 1. 2 times 1 is 2, minus 1 is 1. And I'll do one more. I'll do one more in a color that I have not used yet. Let's see, this purple. If x is 2, then y is going to be 2 times 2. Now our x is 2 minus 1. Minus 1. So that is 4 minus 1 is equal to 3. So fair enough. I just kind of sampled this relationship. I said, okay, this describes a general relationship between a variable y and a variable x. And then I just made it a little bit more concrete. I said, okay, well then if x is one of these for each of these values of x, what would be the corresponding value of y? And what Descartes realized is that you could visualize this. One, you could visualize these individual points, but that could also help you in general to visualize this relationship. And so what he essentially did is he bridged the worlds of this kind of very abstract symbolic algebra and geometry, which was concerned with shapes and sizes and angles. So over here you have the world of geometry. And obviously there are people in history, maybe many people who history may have forgotten, who might have dabbled in this. But before Descartes, it's generally viewed that geometry was Euclidean geometry. And that's essentially the geometry that you study in a geometry class in 8th or 9th grade or 10th grade in a traditional high school curriculum. And that's the geometry of studying the relationships between triangles and their angles and the relationships between circles, and you have radii, and then you have triangles inscribed in circles and all the rest. And we go into some depth in that in the geometry playlist. But Descartes says, well, I think I can represent this visually the same way that Euclid was studying these triangles and these circles. He said, well, why don't I, if we view a piece of paper, if we think about a two-dimensional plane, you could view a piece of paper as kind of a section of a two-dimensional plane. We call it two dimensions because there's two directions that you could go in. There's the up-down direction. That's one direction. So let me draw that. I'll do it in blue because we're trying to visualize things. So I'll do it in the geometry color. So you have the up-down direction. You have the up-down direction, and you have the left-right direction. That's why it's called a two-dimensional plane. If we're dealing in three dimensions, you would have an in-out dimension. In-out. And it's very easy to do two dimensions on the screen because the screen is two-dimensional. And he says, well, you know, there are two variables here, and they have this relationship. So why don't I associate each of these variables with one of these dimensions over here? And by convention, let's make the y variable, which is really the dependent variable. The way we did it, it depends on what x is. Let's put that on the vertical axis. And let's put our independent variable, the one where I just randomly picked values for it to see what y would become, let's put that on the horizontal axis. And it actually was Descartes who came up with a convention of using x's and y's, and we'll see later z's in algebra so extensively as unknown variables, or the variables that you're manipulating. But he says, well, if we think about it this way, if we number these dimensions, so let's say that in the x direction, let's make this right over here. This right over here is -3. Let's make this -2. This is -1. This is 0. Now I'm just numbering the x direction, the left-right direction. Now this is +1. This is +2. This is +3. And we could do the same in the y direction. So let's see, so this could be, let's say this is -5, -4, -3, actually let me do it a little bit neater than that. Let me clean this up a little bit. So let me erase this and extend this down a little bit so I can go all the way down to -5 without making it look too messy. So let's go all the way down here. And so we can number it. This is 1, this is 2, this is 3, and then this could be -1, -2, and these are all just conventions. It could have been labeled the other way. We could have decided to put the x there and the y there and make this the positive direction and make this the negative direction, but this is just the convention that people adopted, starting with Descartes. -2, -3, -4, and -5. And he says, well, I think I can associate each of these pairs of values with a point in two dimensions. I can take the x coordinate, I can take the x value right over here, and I say, okay, that's -2. That would be right over there along the left-right direction. I'm going to the left because it's negative. And that's associated with -5 in the vertical direction. So I say the y value is -5. And so if I go 2 to the left, and 5 down, I get to this point right over there. So he says, these two values, -2, -5, I can associate it with this point in this plane right over here, in this two-dimensional plane. So I'll say that point has the coordinates, tells me where to find that point, -2, -5. And these coordinates, they're called Cartesian coordinates, named for René Descartes. He's the guy that came up with these. He's associating all of a sudden these relationships with points on a coordinate plane. And then he says, well, okay, let's do another one. There's this other relationship where I have when x is equal to -1, when x is equal to -1, y is equal to -3. So x is -1, y is -3. That's that point right over there. And the convention is, once again, when you list the coordinates, you list the x coordinate, then the y coordinate. And that's just what people decided to do. -1, -3. That would be that point right over there. And then you have the point when x is 0, y is -1. When x is 0, right over here, which means I don't go to the left or the right, y is -1, which means I go 1 down. So that's that point right over there, 0, -1, right over there. And I could keep doing this. When x is 1, y is 1. When x is 1, y is 1. When x is 2, y is 3. When x is 2, y is 3. Actually, let me do that same purple color. When x is 2, y is 3. 2, 3. And then this one right over here in orange was 1, 1. And this is neat by itself. I essentially just sampled possible x's. But what he realized is not only do you sample these possible x's, but if you just kept sampling x's, if you tried sampling all the x's in between, you would actually end up plotting out a line. So if you were to do every possible x, you would end up getting a line that looks something like that, right over there. And any any relation, if you pick any x and find any y, it really represents a point on this line. Or another way to think about it, any point on this line represents a solution to this equation right over here. So if you have this point right over here, which looks like it's about x is 1.5, y is 2. So let me write that, 1.5, comma 2. That is a solution to this equation. When x is 1.5, 2 times 1.5 is 3, minus 1 is 2. That is right over there. So all of a sudden, he was able to bridge this gap or this relationship between algebra and geometry. We can now visualize all of the x and y pairs that satisfy this equation right over here. And so he is responsible for making this bridge. And that's why the coordinates that we use to specify these points are called Cartesian coordinates. And as we'll see, the first type of equations we will study are equations of this form over here. And in a traditional algebra curriculum, they're called linear equations. Linear equations. And you might be saying, well, okay, this is an equation. I see that this is equal to that. But what's so linear about them? What makes them look like a line? And to realize why they are linear, you have to make this jump that René Descartes made. Because if you were to plot this using Cartesian coordinates on a Euclidean plane, you will get a line. And in the future, we'll see that there's other types of equations where you won't get a line. Well, you'll get a curve or something kind of crazy or funky. In this video, we're going to learn how to take the distance between any 2 points in our xy coordinate plane. And what you're going to see, it's really just an application of the Pythagorean theorem. So let's start with an example. Let's say I have the point. I'll do it in a darker color so we can see it on the graph paper. Let's say I have the point 3, -4. So if I were to graph it, I'd go 1, 2, 3, and then I'd go down 4. 1, 2, 3, 4. Right there is 3, -4. And let's say I also have the point 6, 0. 6, 0. So 1, 2, 3, 4, 5, 6. And then there's no movement in the y direction. We're just sitting on the x-axis. The y coordinate is 0. So that's 6, 0. And what I want to figure out is the distance between these 2 points. How far is this blue point away from this orange point? And at first you're like, gee, Sal, I don't think I've ever seen anything about how to solve for a distance like this. And what are you even talking about? The Pythagorean theorem? I don't see a triangle there. And if you don't see a triangle, let me draw it for you. Let me draw the triangle. Let me draw this triangle right there. Just like that. Let me actually do several colors here just to really hit the point home. So there's our triangle. And you might immediately recognize this is a right triangle. This is a right angle right there. The base goes straight left to right. The right side goes straight up and down. So we're dealing with a right triangle. So if we could just figure out what the base length is and what this height is, we could use a Pythagorean theorem to figure out this long side, the side that is opposite the right angle, the hypotenuse. This right here, the distance is the hypotenuse of this right triangle. Let me write that down. The distance is equal to the hypotenuse of this right triangle. So let me draw it a little bit bigger. So this is the hypotenuse right there. And then we have the side on the right, the side that goes straight up and down. And then we have our base. Now, how do we figure out? Let's call this d for distance. That's the length of our hypotenuse. How do we figure out the lengths of this up and down side and the base side right here? So let's look at the base first. What is this distance? You could even count it on this graph paper. But here we're at x is equal to, let me do it in the green. Here we're at x is equal to 3. And here we're at x is equal to 6. Right? We're just moving straight right. This is the same distance as that distance right there. So to figure out that distance, it's literally the end x point. And you can actually go either way, because you're going to square everything. So it doesn't matter if you get negative numbers. So it's going to be 6. It's going to be, the distance here is going to be 6 minus 3. Right? 6 minus 3. That's this distance right here, which is equal to 3. So we figured out the base. And just to remind ourselves, that is equal to the change in x. That was equal to your finishing x minus your starting x. 6 minus 3.
This is our delta x. Now, by the same exact line of reasoning, this height right here is going to be your change in y. That's going to be your change in y. Up here, you're at y is equal to 0. That's kind of where you finish. That's your higher y point. And over here, you're at y is equal to negative 4. So change in y is equal to 0 minus negative 4. I'm just taking the larger y value minus the smaller y value, the larger x value minus the smaller x value. But you're going to see we're going to square it in a second. So even if you did it the other way around, you get a negative number, but you still get the same answer. So this is equal to 4. So this side is equal to 4. You could even count it on the graph paper if you like. And this side is equal to 3. And now we can do the Pythagorean theorem. The Pythagorean theorem. This distance is the distance squared. Be careful. The distance squared is going to be equal to this delta x squared, the change in x squared, plus the change in y squared. Plus the change in y squared. This is nothing fancy. Sometimes people will call this the distance formula. It's just the Pythagorean theorem. This side squared plus that side squared is equal to hypotenuse squared, because this is a right triangle. So let's apply it with these numbers, the numbers that we have at hand. So the distance squared is going to be equal to delta x squared is 3 squared plus delta y squared plus 4 squared, which is equal to 9 plus 16, which is equal to 25. So the distance is equal to, let me write that, d squared is equal to 25. D, our distance, is equal to, you don't want to take the negative square root because you can't have a negative distance. So only the principal root, the positive square root of 25, which is equal to 5. So this distance right here is 5. Or if we look at this distance right here, that was the original problem. How far is this point from that point? It is 5 units away. So what you'll see here, this, they call it the distance formula, but it's just the Pythagorean theorem. And just so you're exposed to all of the ways that you'll see the distance formula, sometimes people will say, oh, if I have 2 points, if I have 1 point, let's call it x1 and y1. So that's just a particular point. And let's say I have another point that is x2, comma y2. Sometimes you'll see this formula, that the distance, you'll see it in different ways, but you'll see that the distance is equal to, and it looks like this really complicated formula, but I want you to see that this is really just the Pythagorean theorem. You see that the distance is equal to x2 minus x1 squared plus y2 minus y1 squared. You'll see this written in a lot of textbooks as the distance formula. Distance formula. And it's a complete waste of your time to memorize it because it's really just the Pythagorean theorem. This is your change in x. And it really doesn't matter which x you pick to be first or second, because even if you get the negative of this value, when you square it, the negative disappears. This right here is your change in y. So it's just saying that the distance squared, remember, if you square both sides of this equation, the radical will disappear. And this will be the distance squared is equal to this expression squared, delta x squared, change in x. Delta means change in. Delta x squared plus delta y squared. Don't want to confuse you. Delta y just means change in y. I should have probably said that earlier in the video. But let's apply it to a couple of more. And I'll just pick some points at random. Let's say I have the point, let's see, 1, 2, 3, 4, 5, 6. Negative 6, comma, negative 4. Negative 6, comma, negative 4. And let's say I want to find the distance between that and 1, comma, 1, 2, 3, 4, 5, 6, 7. And the point 1, comma, 7. So I want to find this distance right here. So it's the exact same idea. We just use the Pythagorean theorem. You figure out this distance, which is our change in x, this distance, which is our change in y. This distance squared plus this distance squared is going to equal that distance squared. So let's do it. So our change in x, you just take, you could, it doesn't matter. I mean, in general, you want to take the larger x value minus the smaller x value, but you could do it either way. So we could write the distance squared is equal to, what's our change in x? So we could, let's take the larger x minus the smaller x. 1 minus negative 6. 1 minus negative 6 squared plus the change in y. The larger y is here. It's 7. 7 minus negative 4. 7 minus negative 4 squared. And I just picked these numbers at random, so they're probably not going to come out too cleanly. So we get that the distance squared is equal to 1 minus negative 6, that is 7. 7 squared. And you'll even see it over here if you count it. You go 1, 2, 3, 4, 5, 6, 7. That's that number right here. That's what your change in x is. Plus 7 minus negative 4. That's 11. That's 11. This is this distance right here. And you can count it on the blocks. We're going up 11. We're just taking 7 minus negative 4 to get a distance of 11. So plus 11 squared is equal to d squared. So let me just take the calculator out. So the distance, let's just take, if we take 7 squared plus 11 squared, it's equal to 170. That distance is going to be the square root of that, right? D squared is equal to 170. So let's take the square root of 170, and we get 13.0, roughly 13.04. So this distance right here, we tried to figure out, is 13.04. Hopefully you found that helpful. Let's say I have the point 3 comma negative 4. So that would be 1, 2, 3, and then down 4. 1, 2, 3, 4. So that's 3 comma negative 4. 3 comma negative 4. And I also had the point 6 comma 1. So 1, 2, 3, 4, 5, 6 comma 1. So just like that. 6 comma 1. In the last video, we figured out that we could just use the Pythagorean theorem if we wanted to figure out the distance between these 2 points. We just drew a triangle there and realized that this was the hypotenuse. In this video, we're going to try to figure out what is the coordinate of the point that is exactly halfway between this point and that point. So this right here is kind of the distance, the line that connects them. Now, what is the coordinate of the point that is exactly halfway in between the two? What is this coordinate right here? It's something comma something. And to do that, let me draw it really big here, because I think you're going to find out that it's actually pretty straightforward. At first, it seems like a really tough problem. Gee, let me use the distance formula with some variables. But you're going to see it's actually one of the simplest things you'll learn in algebra and geometry. So let's say that this is my triangle right there. That is my triangle right there. This right here is the point 6 comma 1. This down here is the point 3 comma negative 4. And we're looking for the point that is smack dab in between those 2 points. What are its coordinates? And it seems very hard at first. But it's easy when you think about it in terms of just the x and the y coordinates. What's this guy's x coordinate going to be? This out here, this line out here represents x is equal to 6. This over here, let me do it in a little darker color. This over here represents x is equal to 6. This over here represents x is equal to 3. What will this guy's x coordinate be? Well, he's going to be his x coordinate is going to be smack dab in between the two x coordinates. Right? This is x is equal to 3. This is x equal to 6. He's going to be right in between. This distance is going to be equal to that distance. His x coordinate is going to be right in between the 3 and the 6. So what do we call the number that's right in between the 3 and the 6? Well, we could even call that the midpoint. Or we could call it the mean or the average, or however you want to talk about it. We just want to know what's the average of 3 and 6. So to figure out this point, the point halfway between 3 and 6, you literally just figure out 3 plus 6 over 2, which is equal to 4.5. So this x coordinate is going to be 4.5. Let me draw that on this graph. 1, 2, 3, 4.5. And you see it's smack dab in between. That's its x coordinate. Now, by the exact same logic, this guy's y coordinate is going to be smack dab between y is equal to negative 4 and y is equal to 1. Right? It's just going to be right in between those. So this is the x right there. The y coordinate is just going to be right in between y is equal to negative 4 and y is equal to 1. So you just take the average. 1 plus negative 4 over 2. That's equal to negative 3 over 2. Negative 3 over 2. Or you could say negative 1.5. Negative 1.5. So you go down 1.5. It is literally right there. So just like that, you literally take the average of the x's, take the average of the y's, or maybe I should say the mean to be a little bit more specific, a mean of only 2 points, and you will get the midpoint of those two points, the point that's equidistant from both of them. It's the midpoint of the line that connects them. So the coordinates are 4.5, comma, negative 1.5. Let's do a couple more of these. These actually you're going to find are very, very straightforward. But just to visualize it, let me graph it. Let's say I have the point 4, negative 5. So 1, 2, 3, 4, and then go down 5. 1, 2, 3, 4, 5. So that's 4, negative 5. And I have the point 8, comma 2. So 1, 2, 3, 4, 5, 6, 7, 8, comma 2. 8, comma 2. So what is the coordinate of the midpoint of these 2 points, the point that is smack dab in between them? Well, we just average the x's, average the y's. So the midpoint is going to be the x values are 8 and 4. So it's going to be 8 plus 4 over 2. And the y value is going to be, well, we have a 2 and a negative 5. So you get 2 plus negative 5 over 2. And what is this equal to? This is 12 over 2, which is 6, comma, 2 minus 5 is negative 3. Negative 3 over 2 is negative 1.5. So that right there is the midpoint. Is the midpoint. You literally just average the x's and average the y's, or find their mean. So let's graph it just to make sure it looks like the midpoint. 6, negative 5. 1, 2, 3, 4, 5, 6. Negative 1.5. Negative 1, negative 1.5. Yep, looks pretty good. It looks like it's equidistant from this point and that point up there. Now, that's all you have to remember. Average the x, or take the mean of the x, or find the x that's right in between the two. Average the y's. You got the midpoint. What I'm going to show you now is what's in many textbooks. They'll write, oh, if I have the point x1, y1, and then I have the point, actually I'll just stick in yellow. It's kind of painful to switch colors all the time. And then I have the point x2, y2. Many books will give you something called the midpoint formula, which once again, I think is kind of silly to memorize. Just remember, you just average, find the x in between, find the y in between. So midpoint formula, what they'll really say is the midpoint. So maybe we'll say the midpoint x, or maybe I call it this way. I'm just making up notation. The x midpoint and the y midpoint is going to be equal to, and they'll give you this formula, x1 plus x2, x2 over 2, and then y1 plus y2 over 2, and it looks like something you have to memorize. But all you have to say is like, look, that's just the average or the mean of these two numbers. This is just the average or the mean of these two numbers. I'm just saying I'm adding them to the two together, dividing by 2. Adding these two together, dividing by 2. And then I get the midpoint. That's all the midpoint formula is. So let's say that we have, let me think of a good, say we have 2x plus 3. 2x plus 3 is equal to 5x minus 2. So this might look a little daunting at first. We have x's on both sides of the equations. We're adding and subtracting numbers. How do you solve it? And we'll do it a couple of different ways. The important thing to remember is we just want to isolate an x. Once you've isolated an x, you have x equals something, or x equals something. You're done. You've solved the equation. You can actually go back and check whether that works. So what we're going to do is just do a bunch of operations on both sides of the equation to eventually isolate the x. But while we do those, I actually want to visualize what's occurring. Because I don't want you to just say, oh, what are the rules or the steps of solving equations, and I forgot whether this is allowed or that isn't allowed. If you visualize what's happening, it'll actually be common sense what's allowed. So let's visualize it. So we have 2x right here on the left-hand side. So that's x plus x. And then you have plus 3. Plus 3, I'll do it like this. So that's equivalent to plus 1, plus 1, plus 1. That's the same thing as 3. I could have drawn 3 circles here as well. But let me do the same color. Plus 3. And then that is equal to 5 x's. I'll do that in blue. That is equal to 5 x's. So 1, 2, 3, 4, 5. And I want to make it clear, you would never actually have to do it this way when you're solving the problem. You would just have to do the algebraic steps. But I'm doing this for you so you can actually visualize what this equation is saying. The left-hand side is these two orange x's plus 3. The right-hand side is 5x minus 2. So minus 2 we could write as minus, let me do this in a different color. I'll do it in pink. So minus 2 I'll do as minus 1 and minus 1. Now, we want to isolate the x's on the same side of the equation. So how could we do that? Well, there's two ways of doing it. We could subtract these two x's from both sides of the equation. And that would be pretty reasonable, because then you'd have 5x's minus the 2x's. You'd have a positive number of x's on the right-hand side. Or you could actually subtract 5x from both sides. And that's what's neat about algebra. As long as you do legitimate operations, you will eventually get the right answer. So let's just start off subtracting 2x from both sides of the equation. And when I mean that, I mean we're going to remove 2x's from the left-hand side. And if we remove 2x's from the left-hand side, we have to remove 2x's from the right-hand side. Just like that. So what does that give us? We're subtracting 2x's from the left, and we're also going to subtract 2x's from the right. Now, what does our left-hand side simplify to? We have 2x plus 3 minus 2x. The 2x's cancel out, so you're just left with the 3. And you see that over here. We took two of these x's away. We're just left with the plus 1, plus 1, plus 1. And then on the right-hand side, 5x minus 2x. We have it over here. We have 5x's minus 2x's. You only have 1, 2, 3 x's left over. 3 is equal to 3x. And then you have your minus 2 there. You have your minus 2. So normally if you were to do the problem, you would just have to write what we have here on the left-hand side. So what can we do next? Remember, we want to isolate the x's. Well, we have all of our x's on the right-hand side right here. If we could get rid of this negative 2 off of the right-hand side, then the x's will be alone. They'll be isolated. So how can we get rid of this negative 2? Or if we visualize it over here, this negative 1, this negative 1. Well, we could add 2 to both sides of this equation. Think about what happens there. So if we add 2. So I'm going to do it like this. Plus 1, plus 1. So you can literally see we're adding 2. And then we're going to add 2 to the left-hand side. 1 plus, 1 plus. What happens? Well, let me do it over here as well. So we're going to add 2. We're going to add 2. So what happens to the left-hand side? 3 plus 2 is going to be equal to 5. And that is going to be equal to 3x minus 2 plus 2. These guys cancel out, and you're just left with 3x. And we see it over here. The left-hand side is 1 plus 1 plus 1 plus 1 plus 1. We have 5 ones, or 5. And the right-hand side, we have the 3x's right over there. And then we have the negative 1, plus 1, plus 1. Negative 1, these cancel out. They get us to 0. They cancel out. So we're just left with 5 is equal to 3x. So we have 1, 2, 3, 4, 5 is equal to 3x. Let me clear everything that we've removed so it looks a little bit cleaner. Let me clear that out. And then let me clear, these are all of the things that we've removed. Let me clear that out. And then let me clear that out like that. Edit, clear. So now we are just left with 1, 2, 3, 4, 5. Actually, let me move this over. So edit, cut, edit, paste. So I could just move this over right over here. We now have 1, 2, 3, 4, 5. These are the two that we added here, is equal to 3x's. These guys canceled out. That's why we have nothing there. Now, to solve this, we just divide both sides of this equation by 3. And this is going to be a little hard to visualize over here. But if we divide over here both sides by 3, what do we get? We divide the left by 3. We divide the right by 3. The whole reason why we divided by 3 is because the x was being multiplied by 3. 3 is the coefficient on the x. Fancy word, it literally just means the number multiplying the variable, the variable we're solving for. So these 3's cancel out. The right-hand side of the equation is just x. The left-hand side is 5/3. So 5/3, we could say x is equal to 5/3. And this is different than everything we've seen so far. I now have the x on the right-hand side, the value on the left-hand side. That's completely fine. This is the exact same thing as saying 5/3 is equal to x is the same thing as saying x is equal to 5/3. Completely equivalent. Completely equivalent. We sometimes get more used to this one, but this is completely the same thing. Now, if we wanted to write this as a mixed number, 3 goes into 5 one time with remainder 2. So it's going to be 1 and 2/3. So it's going to be 1 and 2/3. So we could also write that x is equal to 1 and 2/3. And I'll leave it up for you to actually substitute back into this original equation and see that it works out. Now, to visualize it over here, how did you get 1 and 2/3? Let's think about it. Instead of doing 1, I'm going to do circles. I am going to do circles. Actually, even better, I'm going to do squares. So I'm going to have 5 squares on the left-hand side. I'll do it in this same yellow color right here. So I have 1, 2, 3, 4, 5, and that is going to be equal to the 3 x's. X plus x plus x. Now, we're dividing both sides of the equation by 3. We're dividing both sides of the equation by 3. Actually, that's where we did up here. We divided both sides by 3. So how do you do that? Right-hand side's pretty straightforward. You want to divide these 3 x's into 3 groups. That's 1, 2, 3 groups. 1, 2, 3. Now, how do you divide 5 into 3? And they have to be even groups. And here, the answer tells us each group is going to be 1 and 2/3. So 1 and 2/3. So it's going to be 2/3 of this next one. And then we're going to have 1 and 2/3. So this is 1/3. We're going to need another 1. So this is 1 and 1/3. We're going to need one more third. So it's going to be right here. And then we're left with 2/3 and 1. So we've broken it up into 3 groups. This right here, let me make it clear. This right here is 1 and 2/3. 1 and 2/3. And then this right here, this is 1/3. That's another 1/3. So that's 2/3. And then that's 1 right there. So that's 1 and 2/3. And then finally, this is 2/3. And this is 1, so this is 1 and 2/3. So when you divide both sides by 3, you get 1 and 2/3. Each section, each bucket is 1 and 2/3 on the left-hand side. On the left-hand side, or 5/3. And on the right-hand side, we just have an x. So it still works. A little bit harder to visualize with fractions. We have the equation -9 minus this whole expression, 9x minus 6. This whole thing is being subtracted from -9 is equal to 3 times this whole expression, 4x plus 6. Now, a good place to start is to just get rid of these parentheses. And the best way to get rid of these parentheses is to kind of multiply them out. This has a -1. You just see a minus here, but it's really the same thing as having a -1 times this quantity. And here you have a 3 times this quantity. So let's multiply it out using the distributive property. So the left-hand side of our equation, we have our -9. And then we want to multiply the -1 times each of these terms. So -1 times 9x is -9x. And then -1 times -6 is plus 6, or positive 6. And then that is going to be equal to, let's distribute the 3. 3 times 4x is 12x. And then 3 times 6 is 18. 3 times 6 is 18. Now what we want to do, let's combine our constant terms if we can. We have a -9 and a 6 here. On this side, we've combined all of our like terms. We can't combine a 12x and an 18. So let's combine this. So let's combine the -9 and the 6 are 2 constant terms on the left-hand side of the equation. So we're going to have this -9x. So we're going to have -9x plus, let's see, we have a -9 and then plus 6. So -9 plus 6 is -3. So we're going to have a -9x, and then we have a -3. So minus 3 right here. That's the -9 plus the 6. And that is equal to 12x plus 18. Now we want to group all of the x terms on one side of the equation and all of the constant terms, the -3 and the positive 18 on the other side. I like to always have my x terms on the left-hand side if I can. You don't have to have them on the left, so let's do that. So if I want all my x terms on the left, I have to get rid of this 12x from the right. And the best way to do that is to subtract 12x from both sides of the equation. So let me subtract 12x from the right and subtract 12x from the left. Now, on the left-hand side, I have -9x minus 12x. So -9 minus 12, that's -21 negative 21x minus 3 is equal to 12x minus 12x. Well, that's just nothing. That's 0. So I could write a 0 here, but I don't have to write anything. That was the whole point of subtracting the 12x from the left-hand side. And that is going to be equal to, so on the right-hand side, we just are left with an 18. We are just left with that 18 here. These guys canceled out. Now, let's get rid of this negative 3 from the left-hand side. So on the left-hand side, we only have x terms. And on the right-hand side, we only have constant terms. So the best way to cancel out a negative 3 is to add 3. So it cancels out to 0. So we're going to add 3 to the left. Let's add 3 to the right. And we get the left-hand side of the equation. We have the negative 21x, no other x term to add or subtract here. So we have negative 21x. The negative 3 and the plus 3, or the positive 3, cancel out. That was the whole point. Equals, what's 18 plus 3? 18 plus 3 is 21. It's 21. So now we have negative 21x is equal to 21. And we want to solve for x. So if you have something times x and you just want it to be an x, let's divide by that something. And in this case, that something is negative 21. So let's divide both sides of this equation by negative 21. Divide both sides by negative 21. The left-hand side, negative 21 divided by negative 21, you're just left with an x. That was the whole point behind dividing by negative 21. And we get x is equal to, what's 21 divided by negative 21? Well, that's just negative 1. Right? You have the positive version divided by the negative version of itself, so it's just negative 1. So that is our answer. That is our answer. Now let's verify that this actually works for that original equation. So let's substitute negative 1 into that original equation. So we have negative 9. I'll do it over here. I'll do it in a different color than we've been using. We have negative 9 minus, that 1 wasn't there originally, it's there implicitly, minus 9 times negative 1. 9 times, I'll put negative 1 in parentheses, minus 6 is equal to, well, actually, let me just solve for the left-hand side when I substitute a negative 1 there. So the left-hand side becomes negative 9 minus 9 times negative 1 is negative 9 minus 6. And so this is negative 9 minus, in parentheses, negative 9 minus 6 is negative 15. So this is equal to negative 15. And so we get negative 9. Let me make sure I did that. Negative 9 minus 6. Yep, negative 15. So I have negative 9 minus negative 15. That's the same thing as negative 9 plus 15, which is 6. So that's what we get on the left-hand side of the equation when we substitute x is equal to negative 1. We get it equals 6. So let's see what happens when we substitute negative 1 to the right-hand side of the equation. I'll do it in green. We get 3 times 4 times negative 1. 4 times negative 1 plus 6. And so that is 3 times negative 4 plus 6. Negative 4 plus 6 is 2. So it's 3 times 2, which is also 6. So when x is equal to negative 1, you substitute here. The left-hand side becomes 6, and the right-hand side becomes 6. So this definitely works out. We're asked to solve the equation 2x squared plus 3 is equal to 75. So in this situation, it looks like we might be able to isolate the x squared pretty simply, because there's only one term that involves an x here. It's only this x squared term. So let's try to do that. So let me just rewrite it. We have 2x squared plus 3 is equal to 75. I'm going to try to isolate this x squared over here. The best way to do that, or at least the first step, would be to subtract 3 from both sides of this equation. So let's subtract 3 from both sides. The left-hand side, we're just left with 2x squared. That was the whole point of subtracting 3 from both sides. And on the right-hand side, 75 minus 3 is 72. Now I want to isolate this x squared. I have a 2x squared here. So I could have just an x squared here if I divide this side, or really both sides, by 2. Anything I do to one side, I have to do to the other side if I want to maintain the equality. So the left side just becomes x squared, and the right-hand side is 72 divided by 2 is 36. So we're left with x squared is equal to 36. And then to solve for x, we can take the plus or minus square root of both sides. So we could say the plus, or let me write it this way. If we take the square root of both sides, we would get x is equal to the plus or minus square root of 36, which is equal to plus or minus 6. Let me just write that on another line. So x is equal to plus or minus 6. And remember here, if something squared is equal to 36, that something could be the negative version or the positive version. It could be the principal root or it could be the negative root. Both negative 6 squared is 36 and positive 6 squared is 36. So both of these work. And you could put them back into the original equation to verify it. Let's do that. If you say 2 times 6 squared plus 3, that's 2 times 36, which is 72, plus 3 is 75. So that works. If you put negative 6 in there, you're going to get the exact same result, because negative 6 squared is also 36. 2 times 36 is 72, plus 3 is 75. In this video, I'm going to expose you to what is maybe one of at least the top 5 most useful formulas in mathematics. And if you've seen many of my videos, you know that I'm not a big fan of memorizing things, but I will recommend you memorize it, with the caveat that you also remember how to prove it, because I don't want you to just remember things and not know where they came from. But with that said, let me show you what I'm talking about. It's the quadratic formula. And as you might guess, it is to solve for the roots or the zeros of quadratic equations. So let's speak in very general terms, then I'll show you some examples. So let's say I have an equation of the form ax squared plus bx plus c is equal to 0. You should recognize this. This is a quadratic equation where a, b, and c are, well, a is the coefficient on the x squared term, or the second degree term. B is the coefficient on the x term. And then c is, you can imagine, the coefficient on the x to the 0 term, or it's the constant term. Now, given that you have a general quadratic equation like this, the quadratic formula tells us that the solutions to this equation are x is equal to negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. And I know it seems crazy and convoluted and hard for you to memorize right now, but as you get a lot more practice, you'll see that it actually is a pretty reasonable formula to stick in your brain someplace. And you might say, gee, this is a wacky formula. Where did it come from? And in the next video, I'm going to show you where it came from. But I want you to just get used to using it first. But it really just came from completing the square on this equation right there. If you complete the square here, you're actually going to get this solution. And that is the quadratic formula right there. So let's apply it to some problems. So let's start off with something that we could have factored, just to verify that it's giving us the same answer. So let's say we have x squared plus 4x minus 21 is equal to 0. So in this situation, a is equal to, let me do that in a different color. In this situation, a is equal to 1, right? The coefficient on the x squared term is 1. b is equal to 4. b is equal to 4, the coefficient on the x term. And then c is equal to negative 21. The constant term. And let's just plug it in the formula. So what do we get? We get x. This tells us that x is going to be equal to negative b. Negative b is negative 4. Negative 4. I put a negative sign in front of that. Negative b plus or minus the square root of b squared. b squared is 16. Right? 4 squared is 16. Minus 4 times a, which is 1, times c, which is negative 21. So we can put a 21 out there, and that negative sign will cancel out just like that with that. Actually, this is the first time we're doing it. Let me not skip too many steps. So negative 21, just so you can see how it fit in. And then all of that over 2 times a. Over 2 times a is 1, so all of that over 2. So what does this simplify? Or hopefully it simplifies. So we get x is equal to negative 4 plus or minus the square root of, see, we have a negative times a negative. That's going to give us a positive. And we have 16 plus, let's see, this is 4 times 1 is 4 times 21 is 84. 16 plus 84 is 100. Oh, that's nice. It's a nice perfect square. All of that over 2. And so this is going to be equal to negative 4 plus or minus 10 over 2. We could just divide both of these terms by 2 right now. So this is equal to negative 4 divided by 2 is negative 2 plus or minus 10 divided by 2 is 5. So that tells us that x could be equal to negative 2 plus 5, which is 3, or x could be equal to negative 2 minus 5, which is negative 7. So the quadratic formula seems to have given us an answer for this. You can verify just by substituting back in that these do work. Or you could even just try to factor this right here. You say, what two numbers, when you take their product, you get negative 21. And when you take their sum, you get positive 4. Well, so you would get x plus 7 times x minus 3 is equal to negative 21. Notice 7 times negative 3 is negative 21. 7 minus 3 is positive 4. You would get x plus, sorry, it's not negative 21, is equal to 0. There should be a 0 there. So you get x plus 7 is equal to 0, or x minus 3 is equal to 0. X could be equal to negative 7, or x could be equal to 3. So it definitely gives us the same answer as factoring. So you might say, hey, why bother with this crazy mess? And the reason we want to bother with this crazy mess is it'll also work for problems that are hard to factor. And let's do a couple of those. Let's do some hard to factor problems right now. So let's scroll down, get some fresh real estate. Let's rewrite the formula again, just so we have, in case we haven't had it memorized yet. X is going to be equal to negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. Now let's apply this to another problem. Let's say we have the equation 3x squared plus 6x is equal to negative 10. Well, the first thing we want to do is get it in the form where all of our terms are on the left-hand side. So let's add 10 to both sides of this equation. We get 3x squared plus 6x plus 10 is equal to 0. And now we can use the quadratic formula. So let's apply it here. So a is equal to 3. That is a. This is b. And this right there is c. So the quadratic formula tells us the solutions to this equation, the roots of this quadratic function, I guess we could call it. X is going to be equal to negative b. Negative b. B is 6. So negative 6 plus or minus the square root of b squared. B is 6. So we get 6 squared minus 4 times a, which is 3, times c, which is 10. Stretch out the radical a little bit. All of that over 2 times a. 2 times a. 2 times 3. So we get x is equal to negative 6 plus or minus the square root of 36 minus, this is interesting, minus 4 times 3 times 10. So this is minus, let me make sure. Yeah, 4 times 3 times 10. So this is minus 120. Minus 120. All of that over 6. So this is interesting. You might already realize why it's interesting. What is this going to simplify to? 36 minus 120 is what? That's 84. If I'm doing my, 120 minus 36. We make this into a 10. Then this will become an 11. This is a 4. It is 84. So this is going to be equal to negative 6 plus or minus the square root of, but not positive 84. That's if it's 120 minus 36. We have 36 minus 120. It's going to be negative 84. Negative 84. All of that over 6. So you might say, gee, this is crazy. What is this silly quadratic formula you're introducing me to, Sal? It's worthless. It just gave me a square root of a negative number. It's not giving me an answer. And the reason why it's not giving you an answer, or at least an answer that you might want, is because this will have no real solutions. No real solutions. In the future, we're going to introduce something called an imaginary number, which is a square root of a negative number. And then we can actually express this in terms of those numbers. So this actually does have solutions, but they involve imaginary numbers. So this actually has no real solution. We're taking a square root of a negative number. So the b squared, with the b squared minus 4ac, if this term right here is negative, then you're not going to have any real solutions. And let's verify that for ourselves. Let's get our graphing calculator out, and let's graph this. Let's graph this equation right here. So let's get the graph. The y is equal to, that's what I had there before. Let's see, I have 3x. Let me clear this right here. So I get 3x squared plus 6x plus 10. So that's the equation. We're going to see where it intersects the x-axis. Where does it equal 0? So let me graph it. Let's graph it. Notice, this thing just comes down and then goes back up. Its vertex is sitting here above the x-axis, and it's upward opening. It never intersects the x-axis. So at no point will this expression, will this function equal 0. At no point will y equal 0 on this graph. So once again, the quadratic formula seems to be working. Let's do one more example. You can never see enough examples here. And I want to do ones that are, maybe not so obvious to factor. So let's say we get, negative 3x squared plus 12x plus 1 is equal to 0. Now let's try to do it just having the quadratic formula in our brain. So the x's that satisfy this equation are going to be negative b. This is b. So negative b is negative 12 plus or minus the square root of b squared of 144. That's b squared minus 4 times a, which is negative 3, times c, which is 1. All of that over 2 times a, over 2 times negative 3. So all of that over negative 6. This is going to be equal to negative 12 plus or minus the square root of, what is this? The negative times the negative, they cancel out. So I have 144 plus 12. So that is 156, right? 144 plus 12. All of that over negative 6. Now, I suspect we can simplify this 156. We can maybe bring some things out of the radical sign. So let's attempt to do that. So let's do a prime factorization of 156. Sometimes this is the hardest part, simplifying the radical. So 156 is the same thing as 2 times 78. 78 is the same thing as 2 times what? That's 2 times, is that 2 times 39? 2 times 39. So the square root of 156, so the square root of 156 is equal to the square root of 2 times 2 times 39. Or we could say that's the square root of 2 times 2 times the square root of 39, which, and this obviously is just going to be the square root of 4, or this is the square root of 2 times 2 is just 2. 2 square roots of 39, if I did that properly. Let's see, 4 times 39. Yeah, it looks like it's right. 120. Yep. So this up here will simplify to negative 12 plus or minus 2 times the square root of 39. All of that over negative 6. Now we can divide the numerator and the denominator maybe by 2. So this will be equal to negative 6 plus or minus the square root of 39 over negative 3. Or we could separate these two terms out. We could say this is equal to negative 6 over negative 3 plus or minus the square root of 39 over negative 3. Now, this is just a 2 right here, right? These cancel out. 6 divided by 3 is 2. So we get 2. And now notice, if this is plus and we use this minus sign, the plus will become negative and the negative will become positive. But it still doesn't matter, right? We could say minus or plus, or that's the same thing as plus or minus the square root of 39 over 3. I think that's about as simple as we can get this answer. Now, I want to make a very clear point of what I did at that last step. I did not forget about this negative sign. I just said it doesn't matter. It's going to turn the positive into the negative. It's going to turn the negative into the positive. Let me rewrite this. So this right here can be rewritten as 2 plus the square root of 39 over negative 3, or 2 minus the square root of 39 over negative 3. Right? That's what the plus or minus means. It could be this or that, or both of them, really. Now, in this situation, this negative 3 will turn into 2 minus the square root of 39 over 3. Right? I'm just taking this negative out. Here, the negative and the negative will become a positive, and you get 2 plus the square root of 39 over 3. Right? Negative times a negative is a positive. So once again, you have 2 plus or minus the square root of 39 over 3. 2 plus or minus the square root of 39 over 3 are solutions to this equation right there. Let's verify. I'm just curious what the graph looks like. So let's just look at it. So let's look. Let me clear this. Where's the clear button? So we have negative 3x squared plus 12x plus 1. And let's graph it. Let's see where it intersects the x-axis. It goes up there and then back down again. And then, so what are the, so 2 plus or minus the square root. See, square root of 39. Square root of 39 is going to be a little bit more than 6, right? Because 36 is 6 squared. So it's going to be a little bit more than 6. So this is going to be a little bit more than 2. A little bit more than 6 divided by 3 is a little bit more than 2. So you're going to get one value that's a little bit more than 4, and then another value that should be a little bit less than 1. And that looks like the case. You have 1, 2, 3, 4. You have a value that's pretty close to 4. And then you have another value that is a little bit, maybe it looks close to 0, but a little bit less than that. So anyway, hopefully you found this application of the quadratic formula helpful. Use the quadratic formula to solve the equation 0 is equal to negative 7q squared plus 2q plus 9. Now, the quadratic formula, it applies to any quadratic equation of the form, well, we can put the 0 on the left-hand side. 0 is equal to ax squared plus bx plus c. And we generally deal with x's. In this problem, we're dealing with q's. But the quadratic formula says, look, if you have a quadratic equation of this form, that the solutions of this equation are going to be x is going to be equal to negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. And this is actually two solutions here, because there's one solution where you take the positive square root, and there's another solution where you take the negative solution, the negative root. So it gives you both roots of this. So if we look at the quadratic equation that we need to solve here, we can just pattern match. We're dealing with q's, not x's, but it's the same general idea. It could be x's if you like. And if we look at it, negative 7 corresponds to a. That is our a. It's the coefficient on the second degree term. 2 corresponds to b. It is the coefficient on the first degree term. And then 9 corresponds to c. It's the constant. It's the constant. So let's just apply the quadratic formula. The quadratic formula will tell us that the solutions, the q's that satisfy this equation, q will be equal to negative b. b is 2 plus or minus the square root of b squared, of 2 squared, minus 4 times a times negative 7 times c, which is 9, times 9, and all of that over 2a. All of that over 2 times a, which is once again negative 7, which is negative 7. And then we just have to evaluate this. So this is going to be equal to this is going to be equal to negative 2 plus or minus the square root of, see, 2 squared is 4. And then if we just take this part right here, if we take the negative 4 times negative 7 times 9, this negative and that negative is going to cancel out. So it's just going to become a positive number. And 4 times 7 times 9. 4 times 9 is 36. 36 times 7, let's do it up here. 36 times 7, 7 times 6 is 42. 7 times 3, or 3 times 7 is 21, plus 4 is 25. 252. So this becomes 4 plus 252. Remember, this is you have a negative 7 and you have a minus out front. Those cancel out. That's why we have a positive 252 for that part right there. And then our denominator, 2 times negative 7 is negative 14. Now, what does this equal? What does this equal? Well, we have, this is equal to negative 2 plus or minus the square root of, what's 4 plus 252? It's just 256. All of that over negative 14. And what's 256? What's the square root of 256? It's 16. You can try it out for yourself. This is 16 times 16. So the square root of 256 is 16. So we can rewrite this whole thing as being equal to negative 2 plus 16 over negative 14, or negative 2 minus, right? This is plus 16 over negative 14, or minus 16, or minus 16 over negative 14, right? If you think of it plus or minus, that plus is that plus right there. And if you have that minus is that minus right there. Now we just have to evaluate these two numbers. You just have to evaluate them. Negative 2 plus 16 is 14 divided by negative 14 is negative 1. So Q could be equal to negative 1, or negative 2 minus 16 is negative 18 divided by negative 14 is equal to 18 over 14. The negatives cancel out, which is equal to 9 over 7. So Q could be equal to negative 1, or it could be equal to 9 over 7. And you could try these out, substitute these Q's back into this original equation, and verify for yourself that they satisfy it. We could even do it with the first one. So if you take Q is equal to negative 1, negative 7 times negative 1 squared. Negative 1 squared is just 1. So it would be negative 7 times 1, right? That's negative 1 squared. Negative 1 times 2 is minus 2 plus 9. So it's negative 7 minus 2, which is negative 9, plus 9 does indeed equal 0. So this checks out. And I'll leave it up to you to verify that 9 over 7 also works out. Use the quadratic formula to solve the equation negative x squared plus 8x is equal to 1. Now, in order to really use the quadratic equation, or to figure out what our a's, b's, and c's are, we have to have our equation in the form ax squared plus bx plus c is equal to 0. And then if we know our a's, b's, and c's, we'll say that the solutions to this equation are x is equal to negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. So the first thing we have to do for this equation right here is to put it in this form. And on one side of the equation, we have a negative x squared plus 8x. So that looks like the first two terms. But our constant's on the other side. So let's get the constant onto the left-hand side and get a 0 here on the right-hand side. So let's subtract 1 from both sides of this equation. The left-hand side of the equation will become negative x squared plus 8x minus 1. And then the right-hand side, 1 minus 1 is 0. Now we have it in that form. We have ax squared. A is negative 1. So let me write this down. A is equal to negative 1. A is right here. A is equal to negative 1. It's implicit there. You could put a 1 here if you like, a negative 1. Negative x squared is the same thing as negative 1x squared. B is equal to 8. So b is equal to 8. That's the 8 right there. And c is equal to negative 1. And c is equal to negative 1. That's the negative 1 right there. So now we can just apply the quadratic formula. The solutions to this equation are x is equal to negative b. So negative b plus or minus the square root of b squared, of 8 squared, minus 4ac, minus, let me do that in that green color, minus 4, the green's the part of the formula, the colored parts are the things that we're substituting into the formula, minus 4 times a, which is negative 1, times negative 1, times c, which is also negative 1, times negative 1. And then all of that, let me extend the square root sign a little bit further. All of that is going to be over 2 times a. And in this case, a is negative 1. So let's simplify this. So this becomes negative 8. This is negative 8 plus or minus the square root of 8 squared is 64. And then you have a negative 1 times a negative 1. These just cancel out just to be a 1. So it's 64 minus 4. That's just that 4 over there. All of that over negative 2. So this is equal to negative 8 plus or minus the square root of 60. All of that over negative 2. And let's see if we can simplify the expression, the radical expression here, the square root of 60. So let's see. 60 is equal to 2 times 30. 30 is equal to 2 times 15. And then 15 is 3 times 5. So we do have a perfect square here. We do have a 2 times 2 in there. It is 2 times 2 times 15, or 4 times 15. So we could write the square root of 60 is equal to the square root of 4 times the square root of 15, right? Square root of 4 times the square root of 15. That's what 60 is, 4 times 15. And so this is equal to, square root of 4 is 2 times the square root of 15. So we can rewrite this expression right here as being equal to negative 8 plus or minus 2 times the square root of 15. All of that over negative 2. Now, we can divide both of these terms right here are divisible by either 2 or negative 2. So let's divide it. So we have negative 8 divided by negative 2, which is positive 4. So let me write it over here. Negative 8 divided by negative 2 is positive 4. And then you have this weird thing, plus or minus 2 divided by negative 2. And really what we have here is two expressions. But if we're plus 2 and we divide by negative 2, it will be negative 1. And if we take negative 2 and divide by negative 2, we're going to have positive 1. So instead of plus or minus, you could imagine it is going to be, you could imagine it now as being minus or plus. But it's really the same thing, right? It's really now minus or plus. If it was plus, it's not going to be a minus. Now if it's a minus, it's not going to be a plus. Minus or plus 2 times the square root, 2 times the square root of 15. Or another way to view it is that the two solutions here are 4 minus 2 roots of 15 and 4 plus 2 roots of 15. These are both values of x that'll satisfy this equation. And if this confused you what I did, turning a plus or minus into minus plus, let me just take a little bit of a side there. I could write this expression up here. I could write this expression as two expressions. That's what the plus or minus really is. There's a negative 8 plus the square, there's a negative 8 plus 2 roots of 15 over negative 2. And then there's a negative 8 minus 2 roots 15 over negative 2. This one simplifies to negative 8 divided by negative 2 is 4. 2 divided by negative 2 is negative 1. 2 times is 4 minus the square root of 15. And then over here you have negative 8 divided by negative 2, which is 4. And then negative 2 divided by negative 2, which is plus the square root of 15. And I just realized I made a mistake up here. When we're dividing it 2 divided by negative 2, we don't have this 2 over here. This is just a plus or minus the root of 15. We just saw that when I did it out here. So this is minus the square root of 15, and this is plus the square root of 15. So the two solutions for this equation, it's good that I took that little hiatus there, that little aside there. The two solutions, x could be 4 minus the square root of 15, or x could be 4 plus the square root of 15. Either of those values of x will satisfy this original quadratic equation. Determine the number of solutions to the quadratic equation x squared plus 14x plus 49 is equal to 0. And there's a bunch of ways we could do it. We could factor it and just figure out the values of x that satisfy it and just count them. That'll be the number of solutions. We could just apply the quadratic formula. But what I want to do here is actually explore the quadratic formula and think about how we can determine the number of solutions without even maybe necessarily finding them explicitly. So the quadratic formula tells us that if we have an equation of the form ax squared plus bx plus c is equal to 0, that the solutions are going to be, or the solution, if it exists, is going to be negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. Now, the reason why this is two solutions, or the reason why this can be two solutions, is that we have a plus or minus here. If this b squared minus 4ac is a positive number, so let's think about this a little bit. If b squared minus 4ac is greater than 0, what's going to happen? Well, then it's a positive number. It's going to have a square root. And then when you add it to negative b over 2a, or when you add it to negative b, you're going to get one value for the numerator. And when you subtract it from negative b, you're going to get another value in the numerator. So this is going to lead to two solutions. Two solutions. Now, what happens if b squared minus 4ac is equal to 0? If this expression under the radical is equal to 0, you're just going to have the square root of 0. So it's going to be negative b plus or minus 0. And it doesn't matter whether you add or subtract 0, you're going to get the same value. So in that situation, the actual solution of the equation is going to be negative b over 2a. There's not going to be this plus or minus. It's not going to be relevant. So you're only going to have one solution. So if b squared minus 4ac is equal to 0, you only have one solution. And then what happens if b squared minus 4ac is less than 0? Well, if b squared minus 4ac is less than 0, this is going to be a negative number right here. And you're going to have to take the square root of a negative number. And we know if we're dealing with real numbers, you can't take the square root. There is no real number squared that becomes a negative number. So in this situation, there is no solutions, or no real. When I say real, I literally mean like a real number. No real solution. No real solution. So let's think about it in the context of this equation right here. And just in case you're curious of whether this expression right here, b squared minus 4ac, has a name, it does. It's called the discriminant. 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 This is the discriminant. That's that part of the quadratic equation. It determines the number of solutions we have. So if we want to figure out the number of solutions to this equation, we don't have to go through the whole quadratic equation, although it's not that much work. We just have to evaluate b squared minus 4ac. So what is b squared minus 4ac? So b is right here. It's 14. So it's 14 squared minus 4 times a, which is 1, times c, which is 49. That's c right there, times 49. Well, what's 14 times 14? 14, you do it over here. 14 times 14 times 14. 4 times 4 is 16. 4 times 1 is 4, plus 1 is 56. You put a 0. 1 times 14 is 14. It is 691. It's 196. So this right here is 196. And that's what's, well, we can ignore the 1. What's 4 times 49? So 49 times 4. 4 times 9 is 6. Sorry, it's 36, not 46. It's 36. 4 times 4 is 16. Plus 3 is 190, or is 19. So you get 196. So this right here is 196. So b squared minus 4ac is 196 minus 196. So 196 minus 196 is equal to 0. So we're dealing with a situation where the discriminant is equal to 0. We only have one solution. And if you want, you could try to find that one solution. This whole part is just going to be the square root of 0. It's just going to be 0. So the solution is going to be negative b over 2a. And negative b is, we could just solve it. Negative b is negative 14 over 2 times a. A is just 1 over 2. So it's equal to negative 7. That's the only solution to this equation. But if you just wanted to know how many solutions, you just had to find out that b squared minus 4ac is 0. So it's only going to have one solution. And there's other ways. You could have actually factored this pretty easily into x plus 7 times x plus 7 and gotten the same result.